Okay, so we're going to talk about Newton's second law today. Hopefully you're somewhat aware of this. If not, we're going to move kind of quick, so I'm expecting that you've seen something like this before. So real quick, just probably what you're familiar with seeing is that the sum of all external forces, which is a vector, is equal to the mass times the acceleration. And we usually think of mass being constant, even though that's not always the case. And we will do an example where that's not the case. But let's note, in fact, let's do this in a different color, that acceleration is just the derivative of velocity. The time derivative, and when we specify time derivative, you can write it like this. So the little dot, that implies that it's the first time derivative. Now, we can also think of that as being equal to the second derivative of position with respect to time. And using the same logic, we can write it like that. The two dot implies that it's the second derivative. So we can say that force is equal to mass times velocity, or the derivative of velocity, and force is equal to mass times the second derivative of position. Now this is important because normally when you're working with Newton's second law, I don't know, maybe you had like a ramp and you knew this angle and you had like a box sliding down it and stuff like that. You might be able to find the mass of the box or the acceleration. Now with this is helpful because number one, we could find position, or, and here's something interesting, remember that momentum is equal to mass times velocity. So the derivative of momentum is equal to mass, it's an ugly M, v dot. But this is just this. So the big takeaway here is that force is equal to the time derivative of momentum. Okay? It's actually how Newton originally wrote it. Now, let's talk about something called differential equations. And if you haven't experienced differential equations yet, like a course in it, I'm going to talk more about it later. But I just want to give you a brief introduction. I think it's covered in a lot of calculus courses, and eventually you'll have an entire course on differential equations, which is really important in physics. So differential equations is basically just an equation that includes a function, an unknown function, and its derivative. So for example, if we're using r as a position vector, right, that will, in terms of Newton's second law, that includes a function and its derivative, because we can see that you can find force and position, for example. So let's look at an example of a differential equation. And there's a lot of ways of solving this, but we're going to do a very easy one. So this one is a particle moving along x-axis. Oops, jumped on me. Subjected to a constant, so this is an easy example, force F naught. And we'll do a lot more complicated examples, but I just want to get you guys introduced to this. So what do we have? Well, the second time derivative of position is equal to force naught, don't care, Pinterest, divided by mass. Now, because this is the second derivative, we call this a, a second order differential equation. So the order is based on how many derivatives are involved. In this case, there's a second derivative, so it's a second order differential equation. Now, what we could do here is very simply integrate both sides. And what do we get? We get the first time derivative is equal to, well, t, and then what are we evaluating this at from? Well, let's see, this is probably what, from 0 to v naught. Okay? So what stays is just plus v naught, right? So that's our initial, basically we're just saying that, hey, whatever our initial velocity is, whatever it is you're starting with, that's our constant. Maybe an easier way of seeing this without the limits is just this, that v naught equal, or v of time 0 is v naught. And then instead you could think of it as a plus c, but then when you let it equal to 0, right, this would go to 0, c is v naught. Let's not do that though, let's just do this. Oops. And then we can take another derivative, or another antiderivative. And you get x as a function of t is equal to 1/2 f naught over m plus v naught t plus x naught. Hopefully that makes sense. The x naught is using the exact same logic. We would just say x at time 0 is just x naught. Okay? So we have our position function, or position as a function of time, is f naught over m times 1/2 plus v naught t plus x naught. This should look familiar. Should look like x final equals x initial plus v naught t plus 1/2 a t squared. You know what I forgot? T squared. Let's do that. Look at me being silly. Okay. So this works out just fine. And if you're confused, the A is equal to your force divided by your mass, which is just this part. Okay? So we're going to do a few examples using this. Hopefully it makes sense why we're using kinematics, because our force is constant. So we're going to have a constant acceleration. So kinematics would actually work. Not always that easy. Sometimes your force isn't constant. And we'll work through examples like that. But first, I just wanted to talk a little bit about Newton's second law. So hopefully that was